welcome back to the CH1601 video series. The content of this video is largely a revision of the material covered in CH1401. However, not everyone here will have done CH1401, so in this video I will lay out the main concepts regarding atomic orbitals and bonding theory. Bonding is governed by valence electrons in atoms, so it is important to understand the electronic structure of atoms. Electrons are housed in atomic orbitals, and each electron has a unique address, which is composed of 4 quantum numbers. The first quantum number is the principal quantum number, or n for short. I'm sure many of you will be familiar with the traditional model of the atom, the nucleus in the center, with the electronic rings circling around it. The quantum number simply relates to which ring the electron is located within. The lower the principal quantum number, the closer to the nucleus. The second quantum number is the angular momentum number, or L for short. This relates to where electron density is situated in 3D space, giving rise to the specific shapes of atomic orbitals. The lowest angular momentum number, L equals 0, relates to s orbitals. The electron density is restricted to a circular area, so s orbitals are spherical in shape. On paper, we represent s orbitals as a circle. L equals 1 relates to p orbitals, which have 2 lobes of electron density and are often referred to as dumbbell shapes. The area between the 2 lobes is known as the nodal plane. There is no electron density in this region. On paper, we represent p orbitals like this. Of course, there are higher angular momentum quantum numbers. L equals 2 relates to d orbitals, L equals 3 relates to f orbitals, and so on. But s and p orbitals are the main focus of this course. The third quantum number is the magnetic quantum number, or ML for short. This relates to the orientation of any specific orbital in 3D space. Let us first take s orbitals. As spheres, s orbitals can only have one orientation in 3D space, so they only have one magnetic quantum number. Therefore, in each energy level, n equals 1, n equals 2, etc., we can only have one s orbital. Moving on to p orbitals, these can have 3 different orientations in 3D space and 3 magnetic quantum numbers. This means each energy level has 3 p orbitals, px, py, and pz. The fourth and final quantum number is the spin quantum number. This relates to the electron spin within any given orbital. Electrons can either be spin up, they rotate clockwise around their axis, with a spin quantum number of +1/2, or electrons can be spin down. They rotate anti-clockwise on their axis, with a spin quantum number of -1/2. In reality, this essentially means any orbital can have 2 electrons with opposite spins. Electrons fill up atomic orbitals in terms of increasing energy. The lower the principal quantum number, i.e. the closer to the nucleus, the lower the energy. Additionally, the lower the angular momentum number, the lower the energy. In other words, s orbitals are lower in energy than p orbitals, which are lower in energy than d orbitals, and so on. This information can be represented in an energy diagram as shown here. But what happens when we have 3 lots of 2p orbitals, for example? How are these filled? Hund's rule tells us electrons always enter an empty orbital before pairing up. This is similar to how social distancing measures in 2020 mean it is more favourable to space out rather than to get too close to others. As a result, each 2p orbital will be filled singly before any pairing occurs. This is what the theory says, but how does this look in reality? Well, let's take oxygen, for example, which has 8 electrons according to the periodic table. Oxygen's electronic configuration would be 1s2, 2s2, 2p4, if we fill the atomic orbitals up in order of increasing energy. This is an important concept to understand, so let's take a look at a second example. This time, we have a carbon atom with 6 electrons. Carbon's electronic configuration would be 1s2, 2s2, 2p2. Now you, hopefully, have a general understanding of atomic orbitals. We're going to explore how atomic orbitals combine during bonding and form molecular orbitals. This is a very broad topic, which is described by quantum mechanics, but to keep things simple for the purpose of this course, we will only touch upon the basics. Electrons in atomic orbitals can be best described as a wave function, and when we consider these wave functions, they can combine in phase by way of a constructive overlap, or out of phase via a destructive overlap. Therefore, in the linear combination of atomic orbitals, we must consider the phases of atomic orbitals. This is simple for s orbitals because there is only one consistent phase across the sphere. This phase can either be positive or negative, which we usually represent as unshaded or shaded. We can combine two s orbitals of the same phase to create a bonding molecular orbital. This is called an in-phase combination and leads to increased electron density between the two nuclei of the two atoms. However, if we combine two s orbitals of different phases, we create an anti-bonding molecular orbital. This is called an out-of-phase combination, which leads to decreased electron density between the two nuclei, and we actually end up with a nodal plane, a region with no electron density. Because we combine these two s orbitals in an end-on fashion, this is called sigma bonding. We denote the bonding molecular orbital as sigma, and the anti-bonding molecular orbital as a sigma star orbital. The star simply means anti-bonding. We can represent all this information by drawing a molecular orbital diagram. So let's take a molecule of hydrogen, for example, H2. Each hydrogen atom has one electron, each in a 1s atomic orbital. These orbitals can combine in phase to produce a sigma bonding molecular orbital, which is lower in energy and more stable. The orbitals can also combine out of phase to produce a sigma star anti-bonding molecular orbital, which is higher in energy and less stable. By principle, the two electrons go into the lowest energy configuration possible, so they fill the bonding molecular orbital. Things are a little different for p orbitals. As we discussed earlier, p orbitals have one nodal plane. A nodal plane is indicative of a phase change between the lobes. The phase in each lobe can either be positive or negative, which again we usually represent as unshaded or shaded. P orbitals can combine in two different ways, depending on their orientation. Px orbitals combine in an end-on fashion, in what we call sigma bonding, as discussed previously with the s orbitals. The px orbitals can combine in phase to produce a sigma bonding molecular orbital, or out of phase to produce a sigma star antibonding molecular orbital. Py and pz orbitals, on the other hand, combine in a side-on fashion in what we call pi bonding. This is important to understand for alkene and alkyne compounds, which will be discussed in future videos. An in-phase combination produces a pi bonding molecular orbital, while an out-of-phase combination produces a pi star antibonding molecular orbital. In terms of a molecular orbital diagram, let's take an oxygen molecule, for example, O2. Each oxygen atom has 8 electrons, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 4 electrons in the 2p orbitals. The 1s and 2s orbitals of each oxygen atom combine via sigma bonding, as shown here. The 2px orbitals of each oxygen atom can combine via sigma bonding also, while the 2py and 2pz orbitals combine via pi bonding, as depicted here. Try the quiz to test yourself on atomic orbital and molecular orbital concepts.